Beneath the eastern edge of California, something is moving. A monster that has slept for nearly 1,000,000 years is stirring in its colossal grave. The ground cracks, the earth swells, and the headlines all scream the same terrifying message: a supervolcano is waking up. The Long Valley Caldera, responsible for one of the largest eruptions in Earth's history, is showing signs of life. And if it were to repeat its past, it would not be a disaster. It would be an extinction-level event. What does it feel like to be on the verge of the unthinkable? A monster that can bury a city like Los Angeles under a kilometer of hot ash. What do you think is scarier? A monster that's waking up or one that's dying? Let me know in the comments. And a quick, urgent request. A huge number of people who watch these stories never hit subscribe. If you find this important, if you want to understand the forces shaping our world, take 1 second and click that button now. It is the single best way to ensure we can keep making them. Do it now, we'll wait. Let's begin. The story of Long Valley is a story of impossible scale. 760,000 years ago, a chamber of magma bigger than any city swelled beneath the earth. When it finally ruptured, it didn't just erupt, it detonated. 650 cubic kilometers of molten rock and ash were launched into the atmosphere at supersonic speeds. That is nearly 150 cubic miles of material. To put that in terms, that means something. It is enough rock to bury the entire state of Rhode Island half a mile deep. Enough ash to blanket the western United States, reaching as far as Nebraska, in a suffocating gray twilight. The sky went dark. The air turned to poison. The ground collapsed, leaving behind a 20-mile wide, 10-mile long collapsed scar on the face of the planet. A caldera. This was not just an eruption. It was a geological reset, an event that altered the climate of the entire planet for years. And the source of that power is still there, sitting just beneath a popular California ski town, breathing quietly. For decades, the story we told ourselves about Long Valley was one of dormancy, a sleeping giant, a relic of a more violent past. That story was a lie, not a deliberate one. It was a story born from the quiet between nightmares. And that quiet ended abruptly in May of 1980. The year 1980 began with a different volcano on everyone's mind. In Washington, Mount St. Helens had just blown its top in a spectacular and deadly eruption that shocked the nation. Geologists and the public were suddenly on high alert. The comfortable assumption that American volcanoes were tame, predictable things had been vaporized in an instant. And then, just days after the St. Helens eruption, the ground in eastern California started to shake. Violently, a swarm of earthquakes ripped through the Mammoth Lakes region, a scenic resort town nestled right on the southwestern edge of the Long Valley Caldera. This wasn't a minor tremor. This was a barrage. 4 separate earthquakes measuring magnitude 6.0 struck within just a few days. The ground heaved, buildings swayed, and a community that thought its greatest threat was a bad ski season suddenly found itself living on top of an active fault zone inside a supervolcano that seemed to be waking from its slumber. But the quakes were only the beginning. The real alarm bells started ringing when scientists at the U.S. Geological Survey looked at the ground deformation data. They discovered something deeply unsettling. A section of the caldera floor, an area known as the resurgent dome, had begun to swell upwards. By a lot. It was as if something massive underground was taking a deep breath. Something was pushing the surface up from below. The inevitable conclusion was terrifying. New magma could be rising into the chamber. The monster was not just stirring. It was potentially refilling. David P. Hill, who would later become the scientist in charge of the USG's Long Valley Observatory, was one of the key figures trying to make sense of the chaos. He and his colleagues were facing an impossible dilemma. On one hand, the data was screaming a warning. Earthquakes, ground uplift, a known supervolcano. The pattern was undeniable. On the other hand, How do you warn people about a threat that is almost too large to comprehend without causing a full-blown panic? If you live near any kind of geological wonder, a volcano, a fault line, let us know what it's like in the comments below. We read them all. In May of 1982, the USGs made a decision that would haunt the region for years. They issued a Notice of Potential Volcanic Hazards, a carefully worded but unmistakable alert that the caldera was restless and an eruption was a possibility. The notice was intended to inform and prepare. The effect was immediate and catastrophic. Tourists fled. Real estate values in Mammoth Lakes crashed overnight. The local economy, built entirely on the idea that this was a safe and beautiful place to visit, was devastated. Town hall meetings became screaming matches. Scientists were accused of fear-mongering, of destroying a community to cover their own liability in a post-St. Helens world. The bond of trust between the scientists and the town was shattered. But the volcano didn't care about public opinion. The ground kept moving. Over the next 2 decades, the resurgent dome would rise by a total of 80 centimeters, nearly 3 feet. The caldera was breathing. But was it inhaling, gathering strength for a new eruption? Or was it exhaling, a slow release of ancient pressure? That question hung over the region for 40 years. Periods of intense inflation, like the one from 2011 to 2021 where the ground rose steadily, were followed by periods of deflation, like from 2021 into 2026, when the caldera seemed to sigh, sinking by 6 centimeters. This constant, rhythmic movement kept everyone on edge. Every earthquake swarm, every millimeter of uplift was scrutinized. Was this it? Was this the beginning? The media would run stories of the waking supervolcano, and the fear from 1982 would come rushing back. The town of Mammoth Lakes, with its ski slopes and condos, was built entirely inside the collapsed mouth of the volcano. Residents lived with a constant, low-grade hum of anxiety. They were living, quite literally, in the belly of the beast. They needed answers, not just speculation. And the USGs, for all its sophisticated monitoring, could only watch the surface. They could measure the effects. They couldn't see the cause. The magma chamber itself, the heart of the monster, was a black box, sitting 10 kilometers beneath their feet, shrouded in solid rock and mystery. To understand the future, they had to see inside it. A task that was, by every known measure, impossible, or it used to be. The problem with a supervolcano is its scale. How do you map a chamber of magma that is miles wide and buried under 10 kilometers of solid rock? You can't drill into it. You can't see it. For decades, scientists relied on indirect methods, reading the faint seismic waves from distant earthquakes as they passed through the chamber. It was like trying to understand the shape of a building by listening to echoes in a storm. The image was fuzzy, incomplete, and open to interpretation. To truly understand the threat, they needed a new kind of eye, an instrument that could pierce through the bedrock and deliver a high-resolution image of the beast in its lair. They needed a geological CAT scan. The challenge seemed insurmountable. Then, a team of geophysicists at the California Institute of Technology, led by Dr. Zhongwen Zhan, had an audacious idea. What if they didn't need to build a new instrument at all? What if the instrument was already there, buried in the ground all around the caldera, completely ignored? If you find this story as fascinating as I do, take a moment to share it with someone you know, maybe a friend or family member who loves these deep dives. And hitting that like button tells us to make more just like this. The modern world is threaded with a nervous system of glass. Hundreds of thousands of miles of fiber-optic cables carrying our emails, our phone calls, our streaming videos. A sprawling network of telecommunications infrastructure crisscrossing the continent in shallow trenches. John's team saw this network not as a way to carry data, but as a way to listen to the Earth. They pioneered a technique called distributed acoustic sensing, or DAS. The principle is stunningly elegant. A laser is shot down a fiber-optic cable. As the light travels, tiny imperfections in the glass reflect a minuscule amount of that light back to the source. It's a constant, steady signal. But if the ground moves, even by a nanometer, the glass fiber stretches or compresses, changing the timing of those reflections. The cable itself becomes a sensor. Suddenly, a single 100-kilometer stretch of commercial internet cable, the same kind of cable that brings Netflix to the houses around Mammoth Lakes, was transformed into an array of 10,000 individual high-fidelity seismometers. It was a revolutionary leap. They weren't just placing a few dozen sensors on the surface anymore. They were hijacking the planet's digital infrastructure and turning it into a continent-sized stethoscope, holding it against the chest of the supervolcano and listening to its every heartbeat. For a year and a half, the Caltech team, including lead author Dr. Ettore Biondi, listened. They recorded everything. The faintest tremors, the microscopic shifts in the crust, the geological whispers that were too quiet for conventional seismometers to even register. They cataloged over 2,000 tiny seismic events, most of them completely imperceptible to humans. Each tiny quake was a flashbulb, illuminating a tiny piece of the structure deep below. By analyzing how the seismic waves from these microquakes traveled through the Earth, they could begin to build a picture. A wave that travels through solid rock moves at a different speed than one that travels through liquid magma. It was like a colossal ultrasound. They were using sound, not light, to see in the dark. For 18 months, they patiently assembled the data, pixel by pixel, stitching together thousands of tiny acoustic snapshots into a single, cohesive, three-dimensional map. It was the first ever high-resolution image of the Long Valley magma chamber. The world was about to see the monster's face for the very first time. No one was prepared for what it would show. The report was published in the journal Science Advances on October 18, 2023, and it changed everything. The result of the Caltech study was not just a refinement of old theories. It was a complete upending of the entire narrative. The story of the waking giant, the refilling magma chamber, the imminent supereruption, it was all wrong. The high-resolution 3D map created by the DAS network showed something that no one had ever been able to prove before. The top of the magma chamber was not a seething pool of liquid rock ready to blow. It was solidifying. The map revealed a thick, semi-rigid lid of crystallized rock overlaying the deeper, still molten magma. Just like ice forming on the surface of a freezing lake, the vast magma reservoir was cooling from the top down. The supervolcano wasn't waking up. It was dying. This discovery presented an immediate and profound paradox. If the volcano was cooling off, if it was going to sleep, then why was the ground still swelling? Why were the earthquake swarms getting more frequent? Why did all the signs on the surface point to a system that was becoming more active, not less? The answer, it turned in, was far more complex and in some ways more unsettling. As magma cools, it doesn't just turn into inert rock. It undergoes a fundamental chemical change. The process is called crystallization. As the molten silicate cools, mineral crystals begin to form, growing like rock candy in a supersaturated solution. But magma isn't just liquid rock. It's a pressurized slurry of rock, dissolved gases, and a significant amount of water. As the crystals form, they take up less space than the liquid they came from. And they have no room in their structure for the water and gases. So, these volatile components, mostly water and carbon dioxide, get squeezed out. It's like making a snowball. You pack the snow together, and the air and excess water are forced out. Now, imagine that process happening on a geological scale. Under thousands of pounds of pressure per square inch, the cooling magma chamber was releasing enormous quantities of superheated, highly pressurized aqueous fluids. These fluids, much less dense than the surrounding rock, had to go somewhere. So they went up. Suddenly, the breathing of the caldera made perfect sense. The upward swelling of the resurgent dome wasn't caused by new magma pushing up from below. It was caused by these trapped, superheated fluids pushing up on the underside of the crust. The earthquake swarms weren't the result of rock breaking to make way for rising magma. They were the result of these high-pressure fluids fracturing the surrounding rock, creating pathways to escape towards the surface. The constant, rhythmic groaning of the caldera wasn't the sound of a monster waking up. It was the creaking of a colossal pressure cooker venting its steam. The death rattles of a dying giant. I know, this is the second time I'm asking. It feels a bit like a telethon. But it's that important. Our subscriber numbers are how YouTube decides whether to show this to more people. If you haven't yet, please take this one moment and subscribe. The stories we have planned are even wilder than this one. It makes all the difference. So, the panic was over? The headlines were wrong? The people of Mammoth Lakes could finally relax? Not exactly. The revelation that the supervolcano is cooling down did not remove the threat. It simply changed its name. Dr. Zhongwen Zhan, the leader of the Caltech study, clarified the danger. We don't think the region is gearing up for another supervolcanic eruption, he stated. But the cooling process may release enough gas and liquid to cause earthquakes and small eruptions. He then reminded everyone of the events that started it all. For example, in May 1980, there were 4 magnitude 6 earthquakes in the region alone. Those earthquakes weren't a precursor to a super eruption. They were a direct consequence of the cooling process itself. The risk hadn't vanished, it had just been reclassified. The apocalyptic, continent-burying V7 event was likely off the table for the foreseeable future. But in its place was a portfolio of smaller, more localized, and arguably more probable threats. The USCS still classifies the Long Valley Caldera as a very high threat potential volcano. This isn't a contradiction. It's a reflection of the new reality. The primary threat is no longer a cataclysmic magma eruption, but the volatile behavior of the active geothermal system the cooling magma fuels. Think of the magma chamber now as a giant buried nuclear reactor, slowly powering down but still dangerously hot. That heat drives everything. It's what powers the Casa Diablo geothermal plant, which generates enough clean electricity for 40,000 homes. But it's also what could power the next disaster. The release of pressurized gases and fluids can trigger phreatic, or steam-driven, explosions. These are not magma eruptions, but they can still be incredibly violent, hurling rocks and debris over a wide area with little to no warning. There's also the risk of major earthquakes. While the M6 swarms of 1980 were alarming, the system is capable of producing them again and again as the crust continues to shift and fracture under fluid pressure. And then there is the invisible threat. Gas. In the 1990s, an area near Mammoth Mountain began releasing huge, deadly quantities of carbon dioxide gas from the soil, suffocating hundreds of acres of trees and creating a lethal hazard for anyone who might wander into the low-lying areas where the heavy gas accumulated. This CO2 was traced directly back to the underlying magma system. The most likely scenario for a future eruption is not a caldera-forming explosion, but something much smaller, similar to the eruptions that formed the Mono Inyo craters. This chain of younger volcanoes cuts right across the caldera's rim. The most recent of these eruptions was just a few hundred years ago. They were not super eruptions, but they would be utterly devastating if they were to occur in the same area today, which is now populated, developed, and a pillar of California's tourism economy. The terror of Long Valley is not that it will wake up. It is that its process of dying is itself a violent, unpredictable, and decades-long affair. We traded a single, terrifying apocalypse for 1,000 smaller, more insidious hazards. The ground will continue to swell and sink. The earth will continue to shake. The headlines will continue to proclaim a monster waking up, because it is a simpler, more compelling story. But the truth is far more complex. The monster is not waking. It is thrashing in its sleep, and its dying dreams are the things of our nightmares. The third straw is built. The conservation is working. Wait, wrong script. The technology is brilliant. The mystery is solved. And still, none of it guarantees safety. The story of Long Valley has become a profound lesson in the nature of risk. For 40 years, the world was fixated on one question: will it blow? The answer, a quiet and conditional no, feels like a victory, but it is a hollow victory. The Caltech study solved the problem of the supereruption, but in doing so, it illuminated a whole landscape of different, more immediate problems. The town of Mammoth Lakes now finds itself in a strange kind of limbo. The existential threat of planetary annihilation has been lifted, only to be replaced by the more mundane, but no less real, threats of major earthquakes, steam explosions, and poisonous gas releases. Which is worse? A 1 in a million chance of an apocalypse, or a 1 in 1,000 chance of a localized catastrophe that destroys your home, your town, your livelihood? This is the new calculus of survival inside the caldera. The science has removed the ultimate doomsday scenario, but it has not made the ground any more stable. The paradox is that the good news, the magma is solidifying, is the direct cause of the bad news. The ground is still shaking and swelling. And for the last time, I promise, if this journey was worth your time, subscribing is the single best way to support these deep dives. It helps more than you know. Thank you. The human element in this is impossible to ignore. We are drawn to these places of power. We build our towns on their slopes, harness their heat for our power, ski on their dormant flanks. We live in a state of willful denial, celebrating the beauty while ignoring the engine that drives it. The Casa Diablo geothermal plant is a perfect metaphor. We have literally plugged our civilization into the side of the monster, siphoning its fading warmth to power our lights, all while trying to forget that the source of that power is an unpredictable and fundamentally untamable force of nature. The final, unsettling question is not about geology, but about us. The science has given us an unprecedented look into the heart of the volcano. It has replaced a terrifying myth with a complicated and hazardous reality. But what do we do with that knowledge? The emergency plans for a supereruption can be put back on the shelf. But what is the emergency plan for a dying volcano that refuses to go quietly? How does a town prepare for a future where the ground beneath its feet is both a source of life and an engine of potential destruction? The real story of Long Valley is no longer about a waking monster. It is about the much more difficult story of what it means to live in the shadow of a dying one. The clicks and groans from deep within the earth are not the sounds of a beast awakening. They are the sounds